Hello everyone, my name is Madhuri Gupta, working as an assistant professor in the Department of Computer Science, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Welcome everyone to another exciting journey in the world of artificial intelligence. Today we are dealing deep into the fascinating realm of search algorithm and their role in artificial intelligence problem solving. Before that, let's have a quick recap of missionaries cannibals problem. The missionaries and cannibal problem is a classic puzzle that involves safely transporting missionaries and cannibals across a river using a boat while adhering to certain constraints. Here is a quick recap. Problem statement. There are 3 missionaries and 3 cannibals on one side of a river along with a boat that can carry a maximum of 2 people. The goal is to transport all 3 missionaries and all 3 cannibals to the other side of the river without violating the following constraints. At any given time, the number of cannibals on either side of the river should not exceed the number of missionaries, otherwise the cannibals would eat the missionaries. Objective. The objective is to find a series of boat trips that successfully transports all missionaries and cannibals across the river without violating the constraints. So, here is the steps. First, start with 3 missionaries and 3 cannibals on one side of the river along with the boat. Step 2, make a move by taking 2 individuals, either 2 missionaries or 2 cannibals or one of each across the river. The boat must always have at least one person on board. Step 3, ensure that at no point in time on either side of the river the number of cannibals exceeds the number of missionaries. Step 4, repeat the steps until all individuals are safely transported to the other side of the river. So, key insights: solving this problem requires careful consideration of the boat trips to maintain the constraints and ensure the safety of the missionaries. The common approach to solve the puzzle is by using various search algorithms such as depth first search or breadth first search to systematically explore possible states and find a valid sequence of moves. So, our takeaway from the last lecture: the missionaries and cannibals problem serves as a classic example of state space search problem in artificial intelligence. It challenges us to think critically about solving complex puzzles while adhering to specific rules and constraints. The problem highlights the importance of efficient search algorithm and problem solving strategies. At the heart of many AI applications lies the need to search through vast problem space to find solutions, whether it is finding the shortest route or a map or solving puzzles. Search algorithm provide us with the tools to navigate this space efficiently. Let us start our journey by exploring uninformed search algorithms. These are methods that traverse a problem space without utilizing any specific knowledge about the problem. So, what is uninformed search? Uninformed search algorithms are strategies used to traverse or explore a search space without having any specific information about the problem other than the available actions and transitions. Here are some common uninformed search algorithms. First, breadth first search (BFS) explores the search space level by level, visiting all nodes at a certain depth before moving to the next depth level. Guarantees finding the shortest path in unweighted graphs. Second, depth first search (DFS) explores a branch of the search space as deeply as possible before backtracking. May not guarantee the shortest path and can get stuck in deep branches. Third, depth limited search similar to DFS, but limits the depth of exploration to avoid getting lost in deep branches. Helps mitigate the infinite loop issues in cyclic graphs. Fourth, iterative deepening depth first search. Combine the advantages of BFS and DFS by repeating applying DFS with increasing depth limits. Ensure optimal paths and uses memory more efficiently than BFS. Fifth, uninformed cost search. Explore the search space by considering the cost of each path. NQ nodes in the priority queue based on the accumulated path cost. 6. Bidirectional search. Simultaneously explore the search space from both the initial and goal states, meeting in the middle. Reduces the search space and improves efficiency. 7th, backtracking. Recursively explores all possible paths. Backtracking when a dead end is reached, commonly used for problem with constraints optimization. Brute force search. Exhaustively search through all possible states or solutions suitable for problem with a manageable numbers of states. 9th, random search. Generates random sequences of actions to explore the search space. Can be useful in situations where other methods are not applicable or efficient. It is important to note that uninformed search algorithm can be effective in specific contexts, but they may not always be the most efficient or optimal solution. The choice of algorithm depends on the problem's characteristics, constraints and available resources. Using the diagram as shown in the figure, one classic example of uninformed search is breadth first search, BFS. Imagine it as if you are exploring a maze level by level, starting from the initial state and expanding all possible actions before moving to the next depth level. DFS, depth first search, on the other hand, delves deep into the branch of the search tree before backtracking. It's like exploring a single path until you hit a dead end before trying another one. Now, let's elevate our search strategy with informed search algorithms. These methods use domain specific knowledge to guide the search and make more informed decisions. So, what is informed search? Informed search algorithms are strategies that make use of additional information, often in the form of heuristic or estimates, to guide the search process towards the goal more efficiently. Here are some common informed search algorithms. First, greedy best first search expands nodes based solely on their heuristic value, prioritizing nodes that appear closest to the goal according to the heuristic estimate. Second, A star search. Combine the cost of reaching a node, actual path cost, with a heuristic estimate of the cost to the goal. Chooses nodes with the lowest combined cost, ensuring an optimal path when the heuristic is admissible. Third, iterative deepening A, a memory efficient variant of A that employs depth first search with iterative depending and uses a cutoff threshold based on a heuristic. Fourth, sequential heuristic search uses multiple heuristic function to guide the search, often resulting in more informed and efficient exploration. These informed search algorithms leverage domain specific information to make smarter decisions during the search process, often resulting in faster and more efficient exploration of the search space compared to uninformed search methods. The choice of algorithms depends on the problem's characteristics, the quality of the heuristic and the available resources. At the heart of informed search are heuristic function, which estimate the cost from a given state to the goal state. This estimates help algorithm prioritizing promising paths. A star search is a prime example of informed search. It combines the actual cost to reach a state with the heuristic estimate to make intelligent decision about which nodes to expand. Greedy best first search, another informed search algorithm, focuses slowly on the heuristic estimate and chooses the path that appears to the closest to the goal regardless of the path cost. So, whether you are navigating a maze or solving complex puzzles, search algorithms are trusty companions. Uninformed search explores without much prior knowledge, while informed search leverages domain specific wisdom to make more efficient decisions. Remember, AI is like a grand puzzle and search algorithms are our puzzle solving tools. By understanding and mastering these techniques, we unlock the potential to solve a myriad of challenges and pave the way for a smarter and more efficient future. So, here is the relation between breadth first search for graph and tree traversal. Traversal or search for a graph is similar to the breadth first search of a tree. The only catch here is that unlike trees, graph may contain cycles. So, we may come to the sum nodes again. To avoid processing a node more than once, we divide the vertices into two categories, visited and non-visited. A Boolean visited array is used to mark the visited vertices. For simplicity, it is assumed that all vertices are reachable from the starting vertex. BFS uses a queue data structure for traversal. Breadth first search in AI. Follow Explorer of Artificial Intelligence. Today we are embarking on a thrilling journey into the depth of search algorithms, beginning with the ever fascinating breadth first search. Imagine you are in a vast maze, seeking the shortest path to a hidden treasure. Breadth first search is your reliable companion, helping you explore this maze in a systematic and organized manner. Let's say we have a graph with nodes and edges. We begin at initial state, our starting point in the diagram with nodes and edges. BFS expands the initial state, generating all its neighbors nodes. These neighbors represent the possible action or path we can take from the current state. Now, BFS moves to the next layer, exploring all nodes at this depth before progressing to the next layer. It's like mapping out the maze one step at a time. As we continue expanding and exploring, we eventually reach our goal state, making our successful journey through the maze improvise, isn't it? Breadth first search guarantees that we find the shortest path, ensuring we explore all possibilities before venturing deeper. However, keep in mind that BFS toughness comes at a cost. It requires ample memory to store all the nodes in the current layer and become inefficient if the search space is vast. So, there you have it, breadth first search, a reliable companion for navigating complex problem space. By exploring level by level, BFS helps us unveil the hidden games within the vast maze of possibilities. Remember, my fellow adventurers, as you dive into the realm of artificial intelligence and search algorithm, breadth first search is your trusty map or chart the course towards optimal solutions. Here is the breadth first search algorithm. Breadth first search is an uninformed search algorithm that systematically explores a graph or tree level by level, starting from the initial state and moving outward to adjacent nodes before exploring deeper levels. BFS is commonly used to find the shortest path from a starting node to a goal node in unweighted graphs. Here are the algorithm steps. Step 1. Initialize a queue data structure to store nodes yet to be explored. Step 2. Enqueue the initial state, that means starting node, into the queue. Step 3. Create a set or hash table to keep track of visited nodes to avoid revisiting them. Step 4. While the queue is not empty, A. Dequeue a node from the front of the queue. B. If the dequeued node is the goal node, then the search is complete and the path is found. C. If the dequeued node has not been visited, step I, mark the node as visited. Step 2 of the above, generate all possible successor nodes from the current node. Step 3. Enqueue the unvisited successor nodes into the queue. Here are the key points. BFS explores nodes level by level, ensuring that the nodes at a slower depth are visited before moving to deeper levels. BFS guarantees that the shortest path is found because it explores nodes in the order of their distance from the initial state. It is suitable for finding the shortest path in unweighted graphs. BFS is implemented using a queue which follow the first in first out FIFO principle. So, how does BFS work? Starting from the root, all the nodes at a particular level are visited first and then the nodes of the next level are traversed till the nodes are visited. To do this, a queue is used. All the adjacent unvisited nodes of the current level are pushed into the queue and the nodes of the current level are marked visited and popped from the queue. So, here is the illustration. Let us understand the working of the algorithm with the help of following example. Step 1. Initially queue and visited array are empty. In the diagram, queue and visited array are empty initially. Step 2. Push node 0 into queue and mark it visited. In the diagram, push node 0 into queue and mark it visited. Step 3. Remove node 0 from the front of the queue and visit the unvisited neighbors and push them into queue. In the diagram, remove node 0 from the front of queue and visited the unvisited neighbors and push into the queue. Step 4. Remove node 1 from the front of the queue and visit the unvisited neighbors and push them into the queue. In the diagram, remove node 1 from the front of the queue and visited the unvisited neighbors and push. Step 5. Remove node 2 from the front of the queue and visit the unvisited neighbors and push them into queue. In the diagram, remove node 2 from the front of the queue and visit the unvisited neighbors and push them into the queue. Step 6. Remove node 3 from the front of the queue and visit the unvisited neighbors and push them into the queue. As we can see that every neighbors of node 3 is visited. So, move to the next node that are in the front of the queue. In the diagram, remove node 3 from the front of the queue and visit the unvisited neighbors and push them into queue. Step 7. Remove node 4 from the front of the queue and visit the unvisited neighbors and push them into queue. As we can see that every neighbors of node 4 are visited. So, move to the next node that is in the front of the queue. In the diagram, remove node 4 from the front of the queue and visit the unvisited neighbors and push them into queue. Now, queue become empty. So, terminate this process of iteration. So, finally, we have solved the BFS search. So, here are the advantages of BFS. First, guarantees finding the shortest path. Second, suitable for finding solution with the least number of steps. Step 3, advantages 3, simple to understand and implement. So, here are the disadvantages of BFS. May require a significant amount of memory to store the queue and visited nodes, especially in large search spaces. In some cases, BFS may explore many nodes before finding the goal, which can be inefficient. So, here we have another example. Consider the following graph A, B, C, D, E, F. Starting from node A, a BFS traverse would visit the node in the order A, B, C, D, E, F. So, here is the conclusion. BFS is powerful algorithm for exploring and finding the shortest path in unweighted graphs. Its systematic approach guarantees an optimal solution, but might require a trade-off in terms of memory consumption. Understanding BFS is fundamental to grasping the essence of search algorithm in artificial intelligence and computer science. Finding the time and space complexity of breadth-first search. Breadth-first search involves analyzing the number of nodes visited and the memory used during the search. Let us break down the process step by step. So, time complexity of breadth-first search. The time complexity of breadth-first search depends on the number of nodes expanded and the branching factor of the search tree. Let B the average branching factor, let D be the depth of the goal node. In the worst case, BFS explore all nodes at depth 1, then all nodes at depth 2 and so on until it reaches the goal node. Therefore, the total number of nodes expanded is equal to 1 plus b square plus dash 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 plus b to the power d. Using the formula for sum of a generic series, total nodes expanded is equal to b to the power d plus 1 minus 1 divided by b minus 1. Hence, the time complexity of breadth-first search is order of b to the power d, where b is the branching factor and d is the depth of the goal node. Space complexity of breadth-first search. The space complexity of breadth-first search depends on the maximum number of nodes stored in memory at any given time. This includes nodes in the queue and nodes that have been visited. At the first level, BFS stores one node. At the second level, BFS stores two nodes. At the third level, BFS stores 4 nodes and so on. In the worst case, BFS stores all nodes at the maximum depth d in the queue. Since the queue can hold up to b to the power d nodes at this level, the maximum space complexity is order of b to the power d. Note: in a graph with a high branching factor and shallow goal depth, breadth-first search may require significant time and memory. The time and space complexity analysis assumes a tree structure. In a graph with cycles, breadth-first search should keep track of visited nodes to avoid revisiting them. Breadth-first search is a fundamental graph traversal algorithm used in computer science and various applications like graph theory, data mining and network analysis. It explores all the vertices or nodes in a graph in a breadthward motion. That means it starts from the source node and visits all its neighbors before moving on to their neighbors. Here is how BFS works. First, start at a given source node. Next, enqueue, that means add to a queue the source node. Mark the source code as visited to avoid revisiting it. While the queue is not empty, a dequeue that front node from the queue. B. Visit the dequeued node. C and Q all unvisited neighbors of the dequeued node. D. Mark these neighbors as visited. Repeat step 4 until the queue is empty. BFS is often used to solve problems like finding the shortest path between two nodes in an unweighted graph, checking if a graph is bipred, or exploring all reachable nodes in a connected component. It guarantees the shortest path in an unweighted graph because it explores nodes label by label or layer by layer. So, the first time you reach a node, it's guaranteed to be via the shortest path. Here is a Python like pseudocode example of breadth first search. From collection import DQ, DFS define BFS in a bracket graph comma start, which implies that create a queue for BFS and initialize visited array. Q is equal to DQ, visited is equal to set. Next, enqueue the starting node and mark it as visited. Q dot append start, visited dot add start, while Q. DQ a vertex from the queue. Vertex is equal to Q dot pop left. Print vertex, that means process the current node. Next, get all adjacent vertices of the dequeued vertex. For neighboring in graphs vertex, if neighbor not in visited, that means enqueue the neighbor and mark it as visited. Q dot append neighbor, visited dot add neighbor. So, here is one example how we can use it. So, we have graph A which has the neighbor B and C, then we have B which has neighbor A, D, E, we have C, then we have children of C as A and F, then we have D which has neighbor B, then we have E which has neighbor B and F, then we have F which has neighbor C and E. So, this pseudocode demonstrates how BFS traverses a graph from starting node A in this case and prints the node in the order they are visited. Breadth first search offers several advantages, making it valuable algorithm in various scenarios. So, here are the advantages of breadth first search. First, guaranteed shortest path. BFS guarantees that it will find the shortest path from the source node to any other reachable node in an unweighted graph. This property is especially useful in applications where finding the shortest path is essential, such as routing algorithm in computer network. Next is completeness. BFS is a complete algorithm, meaning it will find a solution if one exists. It explores all nodes at a given depth level before moving deeper into the graph, ensuring that it will eventually reach all reachable nodes. Next, find all connected components. BFS can be used to find all connected components in an undirected graph. It identifies all disjoint sets of nodes within the graph, making it helpful in network analysis, social network analysis and clustering problems. Next is identifying bipred graphs. BFS can be used to determine if a graph is bipred, which means it can be divided into two sets of nodes such that no two nodes within the same set are adjacent. This property is essential in various applications including graph coloring and scheduling. Next is exploration of neighbors. BFS is efficient when exploring neighbors of a node. It visits all the neighbors of a node before moving on to their neighbors, which is advantageous in applications like web crawling and web indexing. Next is memory efficiency. BFS typically uses a queue data structure to keep track of nodes to visit. This memory usage is efficient compared to some other algorithms like depth first search, which can be used a stack and may run into issues with deep recursion in large graphs. Next is no need for recursion. Unlike DFS, which is often implemented using recursion and can run into stack overflow issues for large graphs. BFS can be implemented using a loop and a queue, making it more memory efficient and suitable for graphs with a large number of nodes. Next, applications in puzzle solving. BFS is widely used in solving puzzles like 8 puzzle and 15 puzzles and the Rubik's Cube. It systematically explores possible states until it finds a solution, guaranteeing the shortest path to the solution. Can be adapted for many problems. BFS is a versatile algorithm and can be adapted to solve various problems beyond graph traversal, such as finding connected components in an image, generating permutation and more. So, here are some disadvantages of BFS. Despite its advantages, it's important to note that BFS may not be the most efficient choice for all scenarios. For example, in graphs with a large branching factor, the memory requirement of BFS can become significant. Additionally, for weighted graphs where edge weights are considered, other algorithms like Dijkstra algorithm or A star search may be more suitable for finding the shortest path. Breadth first search is a powerful algorithm with several advantages, but it also has limitation and may not be best choice for all scenario. Here are some of the limitation of breadth first search. First, memory uses. Breadth first search can consume a significant amount of memory, especially in graphs with a large number of nodes. It stores all nodes at the current level in a queue until it explores all of them. This memory requirement can be impractical for very large graphs. Next is exponential time complexity. In the worst case, BFS can have exponential time complexity, especially in branching factor heavy graphs. This occurs when there is a large number of neighbors for each node at each level. As a result, the number of nodes to explore grows rapidly, leading to increased time and memory requirements. Next is not suitable for weighted graphs. BFS is designed for unweighted graphs. It does not consider edge weights when finding the shortest path. If the graph has weighted edges, other algorithm like Dijkstra algorithm or A star search or like Dijkstra algorithm or A star search are more appropriate for finding the shortest path. Next, incomplete for infinite graphs. BFS is not suitable for infinite graphs or graphs with cycle that never end. It will keep exploring indefinitely without a clear stopping point. In such cases, depth limited or iterative deepening search may be more appropriate. Next, slower for large graphs. BFS can be slow on very large graphs due to its exhaustive nature. It may take a long time to explore all reaches nodes, making it less practical for certain applications. Next is queue management overhead. Managing the queue data structure in BFS can introduce some overhead, especially when dealing with a large number of nodes. Enqueuing and dequeuing nodes in a queue can have a computational cost. Next is not always suitable for pathfinding in games. In some gaming scenario, especially real-time games, BFS may not be the best choice for pathfinding due to its memory and time requirements. A-star search, which uses heuristic to guide the search, is often performed for such applications. Next is doesn't always find optimal solution in weighted graphs. Even if BFS is adapted for weighted graphs by using a priority queue, it does not guarantee finding the optimal solution in terms of the minimum total edge weight. Dijkstra algorithm or A-star search are better choices for such cases. Despite this limitation, BFS remains a valuable algorithm in various situations, especially when dealing with unweighted graphs or when the goal is find the shortest path without considering edge weights. However, it is essential to consider the characteristics of the problem and the graph at hand to determine whether BFS is the most suitable algorithm or if other alternative would be more efficient or appropriate. In summary, the time complexity of breadth first search is order of b to the power d and the space complexity is order of b to the power d, where b is the branching factor and d is the depth of the shallowest goal node. This complexity helps us understand the efficiency and resource requirements of BFS in solving search problems. Breadth first search is a fundamental graph traversal algorithm used to explore and solve problems in various fields including computer science, artificial intelligence and data analysis. Here is a concise summary of breadth first search. Breadth first search is an uninformed graph traversal algorithm that systematically explores a graph or tree level by level. Starting from a given source node, it explores all immediate neighbors of a node before moving on to their neighbors, ensuring that nodes at shallower level are visited before deeper levels. So, here are the key characteristics. First, queue based approach. BFS uses a queue data structure to keep track of nodes to be explored, following first in first out FIFO principle. Shortest path. BFS guarantees finding the shortest path from the source node to all reachable nodes in an unweighted graph. Third, completeness. BFS is complete for finite graphs, meaning it will eventually find the goal if it exists. Fourth, optimality. BFS provide an optimal solution in terms of the number of edges or steps to reach the goal, but not necessarily in terms of edge, weights or cost. So, we have upcoming lecture on depth first search. So, fellow learners, in our next lecture video, we are diving hand first into the world of depth first search, a fascinating exploration strategy in the realm of search algorithm. Thank you for watching and we will see you in the next lecture.